I wanted to do a short video for you on probably what are two of the most challenging type of problems you'll run into in your Unit 5 exam, and that is titration of a weak acid in the middle of the titration. Well, not exactly in the middle, but during the titration, and then titration of a weak acid at the equivalence point. So this, I just made up this question. It would be a typical type of question. All right, and I just realized as I was talking that I had left out the Ka value. So there it is for acetic acid. So what I would recommend for titration problems is that to look first at what's being titrated. Is it weak or strong? Okay, so if it's strong, all you really need to do is a mole calculation to see how much of the original acid you've added or how much is left, and then do minus log of that. But if it's a weak one, you're going to be in for multiple step calculations. So acetic acid is one of the weak acids, and so what I would recommend doing once you identify it as weak is figuring out quickly how many moles of the analyte and the titrant you have. So, of course, that's just multiplying volume times molarity. And so for part A, well, for both parts, the acetic acid moles, 25 mils times 0.10. So we have 2.5 millimoles of the acetic acid that we are titrating. Right, and now let's figure out how much sodium hydroxide has been added for part A. And so let's see. Sodium hydroxide, at this point we've added 5 mils, and it is 0.2 molar for sodium hydroxide. And so we've added exactly 1 millimole. Now the reason I suggest doing this, you can use these millimole values, well, you're going to use them for your mole table, but I suggest doing this because you need to know where you are in a titration so that you know how to approach the calculation. We're just at a random point here, but remember, just as a little side note, if you're exactly at the halfway point, so if the amount of sodium hydroxide we've been adding was 1.25, exactly half of 2.5, then that would be the situation where the pH would equal pKa and you're done. You don't have to do any more calculations. You just find the pKa of the weak acid. The other point that you need to be aware of is if you are at the equivalence point, okay, that's an extra challenging problem. And you just need to be aware of that ahead of time. So, for example, if we were at the point where the amount of sodium hydroxide was also equal to 2.5 millimoles, then we would know we've reached the equivalence point. It's a totally different way to handle it. So, but right now, we are just someplace during the titration. So we're going to go through the regular steps during the titration of doing a mole table first, and then plugging into Henderson-Hasselbalch. And you should know by now how to write a balanced acid-base reaction. So during a titration, that's what you have going on, acid-base reaction, right? And again, I always leave off the cation on the base. Just it's a spectator and it just gets in my way, confuses things. So really all you have is your weak acid reacting with hydroxide. And the products, of course, are water and the conjugate base of the weak acid. Right, so if I would have decided to leave the cation in, which you can if you want, then of course it would be NaOH instead of OH, right? And would be that, right? The salt. So, all right. So mole table, before, change, after. You can call those 3 rows whatever you want to. It's just what I call them. Okay, so from the last page, we had quickly calculated that we had 2.5 millimoles of the acetic acid, and we had added 1 millimole of the hydroxide. And so whatever the limiting reactant is, which will usually be your titrant, in this case sodium hydroxide, is your lesser amount. You're going to subtract that from both of the reactants to show that they reacted. So the amount of hydroxide you've titrated with will always be 0, assuming you haven't over-titrated. And the amount of the weak acid that you have left is 1.5 millimoles. And we don't care about water, right? And then, let's see, we have made plus 1 millimoles of its conjugate base. All right, so now we have the amount of the original weak acid and the amount of its conjugate base. We can now plug into the Henderson-Hasselbalch equation. pKa plus log of whatever the concentration of the conjugate base is, 1 divided by the acid. Alrighty, and so pH of the titration at this point, 4.57. Here's part B of the problem, and sometimes simply by glancing at the molarity and volumes, you'll be able to tell what point you're at in the titration, and you may have noticed already with this one. But 25 times 0.1 is exactly equivalent to 12.5 times 0.2. So just to kind of prove it to you, in case you don't see it immediately. So we've already done this for the acid, but we have 2.5 millimoles of the acid that we started with, right? And at this point in the titration, 12.5 milliliters of 0.2 molar NaOH equals also 2.5 millimoles of the base. So where you are at this point, you don't even need to do the mole table. I mean, if you identify that you've completely neutralized the weak acid, that you're at the equivalence point, I'm going to show you exactly where to jump to. But just so that it makes a little bit more sense, I'm going to rewrite the titration reaction for you. All right. So at the equivalence point, all of the reactants are gone. They've neutralized each other. And all you have left are the products. Now, water obviously isn't going to affect the pH, so you ignore it. But all you have present is the conjugate base, which is going to make a basic solution, like all bases do, right? So this is the point. If you realize you're at the equivalence point, you don't need a mole table. All you need to do is write out, you're going to treat it like a weak base equilibrium in water, because that's all it is. It is not a titration anymore, okay? So you take the conjugate base, and this would be from last unit, not even from this unit. What if I just gave you a problem and said, what's the pH of this in solution? You would use an ice table. So at the equivalence point, you set up an ice table of the conjugate base. Right? Ice table now. You're in concentrations, not moles. All right, so the first little trick you got to watch out for is getting the correct concentration of the conjugate base. You know how many moles of it you had, right? However many moles you started of the weak acid is the moles you're going to have of the conjugate base. So we know it's 2.5 millimoles. What's the volume? We need to divide by volume to get concentration. The volume of that solution at that point is, you have to add together the volume of the original acid solution and the total amount of the titrant you've added. So the volume at this point is 37.5 milliliters. And so plugging that into my calculator real quickly, 2.5 divided by 37.5, that is 0.067 molar. All right, we'll cross water out. These are 0 to begin with, right? So it's just a regular ice table for a weak base. Minus X plus X. Equilibrium concentration of the conjugate base is now 0.067 minus X. And for the products, X and X. Now, a reminder that X, since it's a base we're dealing with, X is hydroxide concentration. So at the equivalence point, when you're titrating a weak acid, all you're going to have at the end is hydroxide, okay? So now we go ahead and set up the equilibrium constant expression. Again, since we are dealing with a base, we need Kb. We were given Ka in the problem, so at the equivalence point, you've got to convert it to Kb. So that equals Kw, which is 1 times 10 to the minus 14, divided by the given Ka, 1.8 times 10 to the minus 5. So Kb for acetic acid, let me plug that in real quick. Is 5.6 times 10 to the, let's see, 3, 6, 9, 10, minus 10. All right, so we're going to go ahead and set up, so it'd be x squared 0.067 minus x equals Kb. Kb is really small, so we're going to go ahead and neglect the x that is subtracted. Alrighty, and then when we solve for x, so let me calculate what I get real quickly. All right, so x, remember, is hydroxide concentration, so we have to get POH first, and that equals 6.1 times 10 to the minus 6 molar. pH then, sorry I'm running out of room here. pH is minus log of this. So minus log, oh, POH, I'm sorry, POH is minus log of 6.1 times 10 to the minus 6. So that is 5.21. And so pH is 14 minus that. Let's see, what do I get when I do that? That is 8.79. Okay, so we know, we learned at the beginning of this unit, that when you titrate a weak acid, the pH at the equivalence point is greater than 7. And this matches with what we've learned. So hopefully this may have been a little bit helpful to you in working through these very challenging titration of a weak acid.